we will explore several practical continuous random variables, primarily to understand the meaning of their probability density functions. We will introduce the uniform distribution, exponential distribution, gamma distribution, chi-square distribution, normal distribution, and standard normal distribution. Let the random variable x denote the distance in feet between bad records on a used computer tape. Suppose that x is a reasonable probability model that can be described by the probability density function in line 4. To verify that this function f is indeed a probability density function, as shown in the last line, its integral over the entire real axis equals 1. To calculate the probability that the distance between bad records is greater than 40 feet, the calculation expression is shown in line 3. For positive values of x, its distribution function f of x is shown in the last line, which is obtained by integrating the probability density function from negative infinity to x. When x is negative, f of x equals 0. We consider a two-dimensional continuous random vector, x, y, whose joint probability density function is shown in line 1. Given a set A shown in line 2, we want to calculate the probability that the observed value of the random vector, x, y, falls in set A. The calculation expression is shown in the last two lines, which evaluates the double integral of the joint probability density function over set A. Recall that when x is a continuous random variable, the probability of observing any single point is equal to 0, as shown in line 2. Therefore, the expressions in the last two lines should be straightforward to understand. We are going to introduce the uniform distribution. Suppose that the random variable x represents a point selected at random from the closed interval from A to B. If the experiment is performed in a fair manner, it is reasonable that the probability of the point being selected from the closed interval A to x is x minus A over B minus A. That is, the probability is proportional to the length of the closed interval. Therefore, the distribution function of the random variable x can be described as the final mathematical expression. Since this random variable is continuous, when its distribution function f is differentiable, its derivative is the probability density function f. Therefore, we obtain the last line. A random variable x is said to have a uniform distribution when its probability density function is equal to a constant on its support. In particular, when the support is the closed interval from A to B, we obtain the probability density function f shown in the second to last line, in which case the random variable x is denoted as u, a, b. We say that a random variable x has an exponential distribution when its probability density function takes the form shown in line 3, where the parameter theta is strictly positive. At this point, we can also calculate its distribution function f, as displayed in the last line. Suppose that the lifespan of a certain type of electronic component follows an exponential distribution with a mean lifespan of 500 hours. If the random variable x denotes the life of this component, or the time to failure of this component, then the parameter theta is set to 500. Given an observed real number x, the probability that the lifespan of this electronic component exceeds x can be represented by the calculation formula in the last line. Suppose that the electronic component has been in operation for 300 hours. The conditional probability that it will last for another 600 hours is shown in line 4, where the equality follows from the definition of conditional probability. The numerator in the second to last line considers the intersection of the events in the previous numerator, that is, the intersection of events occurring simultaneously. By applying the mathematical expression from the last line of the previous page, the desired probability can be calculated. Before discussing the gamma distribution, we first introduce the gamma function, whose definition is shown in line 3. This gamma function is strictly positive. When t is greater than 1, we can obtain the reduction formula for the gamma function. The equality in line 2 is obtained by using integration by parts. After simplification and rearrangement, we arrive at the reduction formula in the last line. When t takes a positive integer value n, by using the reduction formula of the gamma function, we obtain the expression in line 3. After simple calculations, we arrive at the equality in the last line. We say that a random variable x has a gamma distribution when its probability density function is the mathematical expression in the last line, where theta and alpha are parameters. We will introduce the chi-square distribution, which is obtained by setting the parameters of the gamma distribution to theta equals 2 and alpha equals r over 2, where r is the parameter of the chi-square distribution. Thus, when the probability density function of a random variable x takes the form shown in the third to last line, x is said to follow a chi-square distribution with our degrees of freedom. When the probability density function of a random variable x takes the form shown in line 3, x is said to follow a normal distribution, where mu and sigma are parameters. The parameter mu can be any real number, while the parameter sigma must be a positive real number. In this case, we also say that the random variable x is n mu sigma squared, as displayed in the last line. When a random variable z is n, 0, 1, that is, when the parameter mu equals 0 and the parameter sigma equals 1, we call z a standard normal distribution, whose distribution function is shown in the last line. This theorem states that if the random variable x is n mu sigma squared, then the random variable z in line 2 is n, 0, 1. The proof is as follows. We consider the distribution function of the random variable z as shown in line 2. The first equality is by the definition of z. The second equality converts it to the distribution function of the random variable x, thus yielding the integral in line 3. We use a change of variables to transform the variable x into the variable z, as shown in line 4. The integral after the change of variables is displayed in the second to last line. Upon comparison, we find that this integral is precisely the distribution function of the standard normal random variable z. Thus, it is proved that z is n, 0, 1. This theorem states that if the random variable x is n mu sigma squared, then the random variable v in line 2 will follow a chi-square distribution with 1 degree of freedom. The proof is as follows. The first line shows that v equals z squared, where z is n, 0, 1. First, we consider the distribution function of v, as displayed in line 3. The first equality is by the definition of the distribution function. The second equality follows from the definition of v. The third equality simply solves for z. Since z is n, 0, 1, we obtain the integral in the last line, which considers the probability density function of z. The final equality is obtained by a simple change of variables. We apply a change of variables once more to transform the variable z into the variable y, defined by z equals the square root of y, as shown in line 2. After algebraic simplification, we obtain the integral with respect to y in line 3. Since the random variable v is continuous, the probability density function f of v is the derivative of its distribution function f, that is, f of v equals f prime of v. Because the distribution function f is given in integral form as shown in line 3, we can apply the fundamental theorem of calculus to differentiate the distribution function f, thereby obtaining the probability density function f of the random variable v, as displayed in the last line. Since f is a probability density function, its integral equals 1, as shown in line 2. Using a change of variables, we transform the variable v into the variable x by setting x equal to v over 2, thus obtaining the integral in the second to last line. The final equality uses the form of the gamma function, thereby yielding gamma of 1 over 2 equals the square root of pi. Substituting the square root of pi equals gamma of 1 over 2 into the probability density function f of the random variable v yields the mathematical expression in line 2. Upon comparison, we find that this probability density function f is equal to the probability density function of a chi-square distribution with 1 degree of freedom. Therefore, it is proved that the random variable v indeed follows a chi-square distribution with 1 degree of freedom.